understand it when I get to algebra 2. All right, so we're continuing with this problem because we actually did want to solve this one in terms of y. And so we don't have to just settle for c. Don't settle for c if you can solve for y. And y is our preferred variable to solve for. So all we've got with y is an arctan. We can get rid of that arctan simply by taking the tangent of both sides. So we have y as an implicit function of x. We have arctan y equals e to the x squared plus c. If we take the tangent of both sides, right, tangent and arctan will cancel. We have y equals tangent e to the x squared plus c. Okay? And you cannot factor out the constant c. Okay? So it is trapped in there. So when we're taking the tangent, there may be a constant here with tangent. And it still wouldn't make any difference in terms of our derivative because we take the derivative of the outside and we'd have arctan blop. And we take the derivative of blop, and the derivative of blop is e to the x squared because the derivative of c is still going to be 0. Any questions on it? So now we have an explicit function in terms of y, not an implicit one in terms of x. So our goal is to have it be y equals. We settle for c if we don't have a choice. And if y is squared, we don't have a choice. Can't solve for y.
So that's when it's all
Yeah. But this won't, yeah, that's when we have to settle for solving for c. Because certain equations, and actually all those equations where we're solving for c, they're not functions, they're relations. All right, so here we have dy dx equals e to the negative y sine of x. We want to isolate our variables. So I already moved the dx over, multiply both sides by dx, and then divide by e to the negative y. All right, so now I've got 1 over e to the negative y, which is e to the y. Right? So I just simplified the negative exponent there. E to the y dy equals sine x dx. A real simple integration here. So if we integrate e to the y dy, I get e to the y. And I did show the constant c1 there. If we integrate to sine x dx, we get negative cosine x. We can just combine those constants as one constant. All right, so now I want to solve for y. I don't have to settle for solving for c because we can get the y out of there. As I don't have both x and y trapped as variables. I only have the one. So we're going to take so if I had e to the y and e to the x, that might be a little more complicated, but I just got e to the y. So we're going to take the natural log of both sides. Now cancel out. So I've now got y equals natural log of negative cosine x plus c.
What happened to the e?
It canceled because of the
Okay.
Cancels.
That is
Because the y can move in front, right? Power rule. And the natural log of e is just 1. So I've got 1 times y.
that is wizardry.
So this is the equation, y equals natural log of negative cosine x plus c. Notice that c is trapped in those absolute value bars of natural log. That satisfies the differential equation dy dx equals e to the negative y sine x. Any questions? Good fun? Yeah, mostly it's just, a little bit of algebra isolating and then integrating both sides, and most of the time you'll be able to solve for y. It's when you get a y squared or y to the 4th, then you're just kind of stuck. And those are equations that aren't functions anyway. So if I've got x squared plus y squared equals c, that's the equation of a circle. So a circle is not a function either. So, all right. So autonomous separable differential equations. A differential equation that is autonomous means that the derivative does not depend on the independent variable. So, for example, the equation below is an autonomous equation. There's no x involved. Right? I've got dy dx equals 3y. Right? So it doesn't depend on the x in this one. Right? So you can still separate the y and bring dx to the right. The process is the same. Okay, so here, and I think I added a little extra stuff here. So here I have dy dx equals 3y. Multiply this side by dx, and it looks so strange the way it's written there, and divide both sides by 3y. So notice I left the, because I want to solve for y eventually anyway, you can leave the 3 behind. So here we could just divide by y and leave the 3 behind. It just saves us a step. So if we integrate d1 over y dy, that's natural log of y, and technically there should be parentheses, there should be the absolute value bars there. Now why are there no absolute value bars? Because our goal is to isolate y. So we're going to isolate y, so we're not going to plug in the absolute value bars right there, because it's only going to look like this for a very short while. If we integrate 3 dx, that's 3x, and then we have our plus c. Now to solve for y, all we have to do is take the, instead of taking the log of both sides, we're exponentiating both sides.
I remember that.
Good. Oops. I can't find yellow. It's being blocked. Where the heck is yellow?
You have to put the pen there.
There we go. It's blocking it, right? So we're just that still looks like red.
I think red looks better.
No, not on a dark color. How about now? There we go.
That's not red. That does look better.
Yes. So we'll exponentiate to isolate y when we have ln y. And that word is have. Doesn't work that way. It has 4. All right, so to exponentiate, all we do is we raise our terms to, they become the exponents, and we're e is our base. So we've got e to the natural log of y equals e to the 3x, and the e and natural log will cancel each other out. We've got y equals e to the 3x plus c. The plus c, notice, is an exponent. So this is what our equation is. I just want to make sure it's clear. All right, so our solution here, our general solution, is y equals e to the 3x plus c. That is an exponent.
So then what's the part highlighted? So ln y equals 3x plus c. What's that in relation to? In relation to e ln y.
So you exponentiate it. So
You exponentiate to isolate y.
You raise everything to the e cancels on the ln y. You're left with y, and then you have e to the 3x.
Oh.
You can exponentiate anytime you have a log.
Oh, so that's what.
Yeah.
Gotcha.
And it just, the base is, you'll just match the base of your log. So if my log is natural log, then my base would be e. If it had been log base 2 of x, or 2 of y, then I would have raised it to the second, I would have had 2 to the log base 2 of y.
So can you do the same thing where if everything is raised to e, can you put a natural log?
You can take a log of both sides, yeah. Whatever will isolate our variable. And now we solve for y.
This is easy.
Okay, good. I don't know if I put in this lesson. If not, I'll just add it to the end. There should be
Didn't we do this right? I think we did this on Saturday.
What is it, part of the example ones?
I think so, because I remember we plugged in. We started plugging in for to find c.
No, this one's just an initial value. So here we want to find the exact solution to the following initial value problem. So we have y prime equals 3 plus y, and y of 0 equals 1. Okay? So we're going to rewrite y prime as dy dt. Okay? So here it's a dt because we don't see an x. We can do it as terms of a dt. It could be a dx. This one's going to be a dt. All right, so dy, and it may if be referring to something varying as a function of time. So dy dt equals 3 plus y, because you don't want y prime. You do want, this is called Leibniz notation. So you do want, when you're working with your differential equations, you do want dy dx, dy dt, etc., so you can have a separable. Now, what do you think that says?
Times e.
A separable.
So you can have a separable d times e.
I have no idea what that says.
Separable.
You wrote it, Mr. Shiner.
Separable.
Is it?
I know the word is separable.
Is it dy? Is it supposed to be dy?
What?
Or d?
I figure, but it was
Looks like something got erased there.
Maybe it was
Well,
a
what
play
could
on
it be?
So you
maybe.
I don't know.
dy
There's-
dx, dy dt, etc. So you can have a separable.
There's no knowing, just like the-
Differential equation. There we go.
Oh, that makes sense.
Oh, d.
Oh, we're smart.
Why I abbreviated that. Yeah, separable differential equation. D period, E period. All right, so here we'll multiply both sides by t. We'll divide by 3 plus y. So we have 1 over 3 plus y dy equals dt. All right, so now if we integrate, 1 over 3 plus y becomes natural log of 3 plus y plus c1 equals t plus c2. We've taken the integral of both sides. Now, we can drop the absolute value bars if our goal is to solve for y. I don't know if let me just see if I put that on the next page or not. Otherwise, I'm going to solve it over there.
Yes.
Okay, I did. Good. All right, so first of all, are there any questions on this one? I wanted to see if I left myself room. Okay. All right, so I have natural log 3 plus y equals, I just combined my c's, right? So c is an arbitrary constant, right? So we just put all our c's together here. So we have natural log of 3 plus y equals t plus c. All right, so I'm going to exponentiate to solve for y. So now I've got, so e and natural log will cancel. So I've got 3 plus y. On the other side, I'm exponentiating the t plus c. They become the exponents on my e. So I'm taking both sides and I'm exponentiating. E is the base. Whatever I had there is now the power.
Okay.
All right? On the one side it cancels, and now all I want to do is subtract 3 from both sides, so I isolate my y. Y equals e to the t plus c minus 3. Right? So now we're gonna alter this just a little bit. Yeah. So I'm going to separate these, right? So I can do that because this is just the product rule, right? You just add exponents. To multiply like bases raised to a power. Right? So I can go the other way, and that's what we've done. Right? So e to the t plus c is the same as e to the t times e to the c. C is just a constant. E is a constant. So I've got e to the c is just a constant. I'm going to put a box around it.
Which means it's gone.
No, it's not gone. But I can represent it with any letter I like. I don't have to keep it e to the c, right? Because in the end, it's all going to depend on what c is. This could be any constant at all. So I'm going to replace e to the c with a. A here is just a constant, okay? A is a constant. I've replaced, and it's replacing e to the c, which is also a constant, okay?
So can you only do that when you have a constant and an exponent with a constant? Or
Yes, yeah. Yes, so, yeah, if I have a constant raised to a constant power, yes. I can just replace that with a number.
Doesn't this change the function though? So if you're talking about a
No.
Wait a second. So if you're talking about a family of functions.
Because I'm looking, will it change my function? No, because I've solved for my particular
It's
solution.
the same function. But if you wanted to keep it in terms of family of function, wouldn't keeping it e to the c be better because the c is
No.
changing?
No,
Okay.
because we will never find out. If all I have is the general solution, I will never find out what c is anyway. So it would be better to rewrite that as a single constant. Okay. All right. So all I've done is I've replaced e to the c with a. So now I've got y equals a to the ae to the t minus 3. And I need to solve for, now I have no c whatsoever in this equation. What I need to solve for is a. Okay, so we're solving for a. All right, so we're given some initial condition, I think way back here that I've already forgotten about, that we have written over there, but just to remind people, we were told that y of 0 equals 1. So we're going to replace the t with 0, the y with 1, and solve for a. So, and now I've got a times e to the 0 minus 3. Add 3 to both sides. So now I've got 4 equals a times e to the 0. E to the 0 is just 1. So 4 equals a. So now this is my particular solution. This is the particular solution that has way back here y equal dy dt equals 3 plus y as its differential equation. So the equation that satisfies this differential here, that's what I'm trying to say, that also satisfies, has 0, 1 as a point, is y equals 4e to the t minus 3. That's our particular solution. And this is this introduces a whole important family of differential equations and their solutions.
So you know to plug in 0 because the y equals 1.
Yes, we were given that point, 0, 1 at the beginning. Without being given 0, 1, I can only rewrite it as y equals a times e to the t minus 3.
Okay.
And there's a family of functions where a could be anything.
Now is a good stopping point.
Now's a good stopping point. Okay.
Stupid time.